So let's summarize the one-dimensional kinematics mathematical model that we have derived so far, and then we'll apply it to a simple example. We'll kind of see how it all fits together and works together to actually help us solve problems. So far what we've come up with is this. We have a couple different formulas that we've been able to derive describing the motion of objects that are moving in one dimension. So we have our displacement, you can say, is this. Delta x equals v naught t plus 1/2 a t squared, right? And so this will kind of cover us for the case where we have, tell us what our displacement is, assuming we have some sort of initial velocity and some sort of acceleration. Of course, as we saw before with our examples that we derived this from, if our initial velocity is 0, it just simplifies to 1/2 at squared. If our initial acceleration is 0, then this term goes away and it just simplifies to our distance equals rate times time that we're used to, right? Of course, if both of these are 0, then our displacement is going to just be 0, right? We're just not going to go anywhere. So that's not going to be interesting. It's still true. So just to say that this formula here does kind of cover all of the different cases that we can have as long as we have constant acceleration, right? So this is our kind of formula for our change in position. We also had our formula for our velocity as a function of time, which is our initial velocity plus our acceleration times our time, right? Again, so this is just simply saying if we have our velocity now is equal to whatever our initial velocity was plus our acceleration times our time. So if our velocity is changing at all, right, this kind of term will kind of take care of how how our velocity is changing, right? The higher your acceleration is, the faster your rate of change of your velocity, the more quickly your velocity will change the function of time. Of course, if you don't have any acceleration at all, what is your velocity equal to? It's just going to be the same as your initial velocity, right? Then we also had one more that we know is kind of just definitionally true from the beginning. We can always write our change in position, our displacement is equal to our average velocity times our time, right? If you happen to know what the average velocity is, you can have all different kinds of crazy things going on your trip, but as long as you know what the average velocity is, right, again, it's just the total displacement divided by the total time, this formula also will always be true. And so this one, this isn't redundant. This is actually going to be very useful for us to make sure to keep track that this is correct as well, that we can make use of that one. So these are the three formulas that we've derived so far. Again, all of these are true as long as we have, these two will be true. This one is always true. These two will be true when A is constant. And A can be 0, that's still constant, right? But as long as we have a constant acceleration, then these two formulas here will be valid. Again, this one will always be true, so it's actually just the most general one that we have. But these two are going to work when we have situations where acceleration is constant. The good news for all of us, again, is we do have this case where we are only going to be worrying about problems where our A is constant, right? So what exactly do I mean by that? It's like, how can we have this this be applied to a more concrete situation? So let's do kind of a somewhat simple example here. So we're going to have the situation that we're going to deal with is, I'll give you some information about a car that's driving along. It starts at one stoplight, stops at the next one, and we'll see what all things we can learn about it using these formulas that we have up here. Make sure they're still on the screen. So we can say we have a car driving along and it's sitting at a stoplight initially. So the stoplight's going to turn green, and then after that happens, the car is going to speed up. It's going to drive forward, it's going to hit the accelerator. We're going to speed up at an acceleration of 5 meters per second squared. It's going to do this, for 6 seconds, right? So after this 6 seconds is up, we're going to stop accelerating and we're going to travel at a constant speed then travel at constant velocity for 10 seconds, right? So initially we have some acceleration for this first part, then we're going to stop accelerating, right? So again, that might be throwing you off. Okay, I said acceleration has to be constant. I'm changing up the acceleration on you. It's okay. I'll show you how this works here in a second. So the car speeds up at an acceleration with an acceleration of 5 meters per second squared for 6 seconds. Again, it started at a speed of 0. It was sitting still at the stoplight. Then it's going to travel at a constant velocity for 10 seconds. And then after that, it's going to hit the brakes. So it's going to slow down. Sorry, wrong kind of brakes. I can't spell today. It's going to hit the brakes and stop 50 meters after it initially hit the brakes. So it's going to stop 50 meters later. And what we want to know then is how far was this total trip? And how long did it take? So this is what we're given, right? We have the car speeds up. It's sitting in a stoplight. It speeds up with an acceleration of 5 meters per second squared, and it does this for 6 seconds. It's then going to travel at a constant velocity for 10 seconds, and then afterwards, the car is going to hit the brakes, and it's going to stop 50 meters after it hit the brakes. We want to know how far was the total trip, and we want to know how long did this trip take. So the first thing that we want to do, we'll come back to these equations here in a second, but for now, let's just look at this graphically. So the first thing we want to do then is let's just graph this situation. Let's graph our position, our velocity, and our acceleration as functions of time. Let's graph each of those for all the different parts of this trip that we have. So what does our position as a function of time look like for this car? So initially, what's our initial speed? Again, it's 0. Then we're going to speed up. We're going to travel at a constant rate, and then we're going to slow down. So what that's going to look like is this. So we speed up, then we travel at a constant speed, and then we slow down and come to a stop. I'm going to section it off here and here, and I'll show you why here in a second. Now let's look at our velocity as a function of time. What does our velocity look like as a function of time for this? So we don't know exactly, but just we can kind of get the general idea for what this would look like. We start with a speed of 0, and then we accelerate for some amount of time. Then we travel at a constant speed, so our velocity levels off, and then we slow back down to 0, right? So we start at 0, we speed up, travel, hit the brakes again when we get to the next stoplight, and come to a stop. So our velocity as a function of time will look like this. And then finally, what does our A as a function of time look like? I'm going to draw this one a little bit differently. I'm going to put our 0 there. We'll see why here in a second. So initially, what is our acceleration? Initially, our acceleration is some sort of positive number, right? We have some sort of positive value of this 5 meters per second squared that we are traveling at. After that, we have an acceleration of 0, right? We do that for, I don't know, 10 seconds, right? So for the next part of the trip, our acceleration is 0, and then finally we are slowing down. So of course, then our acceleration finally is going to be negative. So I'm going to put it below this axis here to denote that we do have, at the end of our trip, we have a negative acceleration while we are slowing down. So here's what my 3 graphs are going to look like for my position, my velocity, and my acceleration, right? I'm kind of, in each case, I've sectioned them off into these 3 sections. And the reason I'm doing that is, again, because these formulas that we have here, if I go back up here, these only work when A is constant. And I'm showing you right here on this graph, this A is not constant, right? This A is changing. So how can we do this? Well, what we can do is we can break it up into 3 different sections. We can apply these formulas to each different section along the way. So this section here where we do have constant acceleration, this first part where we're speeding up, we can apply a formula there. We can apply our whole set of formulas there. Then we'll have a different set of formulas to describe what's going on here while we're traveling at a constant rate. And then we'll have a different set of formulas again to describe what is going on at this last part here where we are slowing down. And of course, it'll be true for our V and our A as well. So let's go ahead and let's try and start to solve this problem and see what information we can figure out right away. So again, the first thing we want to know is how far was the whole trip. We want to know how many meters we actually drove. And we also want to know how much time it took for this to happen. So the general strategy that we're going to apply to this then is we are going to say, let's figure out what happens in each of these 3 trips. We'll figure out what happens in the first part, we'll figure out what happens in the second part, we'll figure out what happens in the third part, right? We'll see basically how far and how long do we go at each section, and we can just simply add them all together to figure out what the total trip was. And again, this kind of stuff here going along where I'm breaking it up into these 3 sections, this is also kind of a consequence of the model that we are using, right? Again, we are modeling this car to be a little bit simpler than it actually is, right? If you actually get in your car and you hit the accelerator, what you'll see is you don't have these very defined areas where you have this acceleration, then you immediately switch to this acceleration, then you immediately switch to this acceleration, right? However, we can use our model to approximate what happens, assuming we're just jumping really quickly between various values of acceleration. It's not going to tell us exactly what's going to happen when we're in a car, but it will give us some pretty good results, right? So this is kind of what we mean when we make these models. They are not exact representations, right? Just as we saw with our various models of the atom that we had, and some of them are more accurate, and some of them are less accurate. Now we're having these very simple models for how a car moves, right? We're kind of modeling, we're using model as a verb now. We're modeling how this car is moving, and we're making some simplifying assumptions so that the math stays reasonable for us to do it. But as it turns out, these are going to be very good approximations. This actually does do a pretty good job of describing how simple stuff moves around in this one-dimensional motion, right? So again, let's look at our model. Let's see what it says for these different cases that we have here. So for the first part, let's just figure out that. Let's see what is going on for part 1 of our trip. What are the kinds of things that we would want to know? Well, the first thing that we can do is we can write our formula for what is my total displacement for the first part of my trip. I'm going to say it's delta x1 is what we'll call it, right? So we're going to have several. We'll have delta x1, delta x2, and delta x3. Right now, we're just worried on this first part. We are initially accelerating. Delta x1 is going to be equal to what? My initial speed at the beginning times my total time for trip 1 plus 1/2 my first acceleration times time 1 squared. So I put a lot of subscripts here. Again, it's still our simple formula that we had up here. It's the same one. Delta x equals v naught t plus 1/2 at squared. I'm just now simply applying it to this first part of the trip. So we have delta x1 v naught 1 t1 plus 1/2 a1 t1 squared. What is our initial velocity at the beginning of part 1? It is 0, right? We stopped at this stoplight, so this whole term will go away. We won't have to worry about that. What is our acceleration? We know what that one is. It's this 5 meters per second squared, right? So we do have that. And how long were we accelerating? We were accelerating for 6 seconds. So we know right away we can't actually solve just straightforwardly for this delta x1. It's going to be 1/2 times 5 meters per second squared times 6 seconds squared. And what this distance should give you, this distance should be about 90 meters. What else might we want to know about the first part of our trip? Whoops, sorry, it's off the screen here. This is going to be 90 meters that we went for this first part. So we have this 90 meters for delta x1. We'll keep that in mind. What else might we want to know? Let's figure out how fast we were going at the end of it. Why do I want to know that? Well, that's going to be how fast I'm going at the beginning of part 2. Let's go ahead and let's find that. Let's find the final velocity of part 1, which is again going to be v naught 1 plus a1 t1. Again, our v naught 1, as we saw before, is 0. So this will just be a1 times t1. And our final velocity for part 1 will just be this 5 times 6. So we have a times t, and what we end up with is 30 meters per second for our final velocity for part 1. Let's go ahead and let's look at what is happening with part 2. We'll keep this here as a reference. We'll come back to it if we need to. All right, so then for part 2, what we know delta x1 equals 90 meters, and we know that v final 1, this is an f, equals 30 meters per second. So these are the important pieces of information that we found from part 1. Let's go ahead and let's look at delta x2 then. X2 I can write in the same way. It's v naught 2 times t2 plus 1/2 a2 t2 squared. So now what are my values for this one? So you can say, we can go back, we'll reference this again. So this is part 1. Part 2, we traveled at constant velocity, and we did it for 10 seconds, right? So if we're looking at this stuff here, we're now focused on part 2, this kind of where our v is constant, our position is increasing, but in a constant manner, and our acceleration is 0, right? So this actually gives us this term goes away completely, right? We don't have to worry about that. Our v02 is going to be what? It's going to be the same thing as our final velocity from part 1, right? We're breaking this up into 3 different sections, but it's just one car, right? It drove, it accelerated up to a speed, it maintained that speed thereafter for part 2. So we're going to say delta x2 is 30 meters per second times 10 seconds, right? This is how long we traveled at a constant speed. So this would give us, what, about 300 meters for part 2. And again, as always, make sure to keep track of your units. You have meters per second times seconds. So the seconds cancel out and you do get meters, which is what you want, right? You're solving for a distance, so you'd better be getting meters with your units. So for part 2, we have this 300-meter distance, right? So actually now what we can say is we can already figure out how far was the total trip, right? We can say delta x total is delta x1 plus delta x2 plus delta x3, and this is 90 meters plus 300 meters plus 50 meters, right? Where's the last thing we're told here? We don't know. It's a little bit different for this last part. We'll have to address that here in a second when we find the time. But we're saying for the first part, we know our acceleration and our time. For the second part, we know our time, and we can figure out our speed from the first part. For that last part, we're just given the distance right away. So right away, we can solve for what our total distance is. And what we get is 90 plus 300 plus 50 is about 440 meters. Is our total distance for this trip. So that's the first part that we want. But we also want to know the time, right? We still want to know t total. And how are we going to figure out what that one is? Well, we know what the time for part 1 and part 2 are, right? We have 6 seconds, and then we have 10 seconds. But what we don't know is we do not yet know the time for part 3. So let's take a look at what we can figure out about the time for part 3. Let's go ahead. Let's start as we usually do. Let's write our delta x3. We already know this one, so we know it's going to be 50 meters, but what we don't know is exactly what's going on with this acceleration this time. So we have v0 3 times t3 plus 1/2 a3 t3 squared. So now the issue is we have our one equation, but we actually have 2 unknowns. We don't know t and we don't know a. We do know this distance, but how is this going to help us? Well, if we just leave it as this, we can't really figure out exactly what is going on. But we need to remember we can substitute in for this value here if we remember what our kinematics are, right? If we remember what all of our equations are that we have. What we can say is for part 3, we can also say this. V final of part 3 equals V initial of part 3 plus A3 T3. We can also use this formula. How is this going to help us? Well, so what this is going to do, let's subtract this V initial from part 3 over. So we'll have our V final 3 minus V initial 3 equals A3 T3. And this, of course, gives us what? This gives us delta V for part 3 is A3 T3. How does this help? What is our delta V? What is our change in velocity? Essentially, I'm saying, what is our final velocity, right, from part 3? We already know what the initial velocity from part 3 is. It's got to be this, come back up here, it's got to be this 30 meters per second, right? The final velocity from part 1, we maintained that for part 2. This is also going to be, so this is also our V for part 2. And this is also going to be our initial velocity for part 3. It has to be, right? We accelerated up to this, and we maintained it right up until we started slowing down at the beginning of part 3. So this delta V for part 3 is V final minus V initial for part 3. Our initial for part 3 is positive 30 meters per second. Our final for part 3 is 0, right? We're coming to a stop. So we need to be able to know. Basically, what we're just saying is we know that at the end of this trip, we've come to a stop, right? We've hit the brakes, we've stopped at the next stoplight. So the change in velocity for part 3 is actually just going to be negative 30 meters per second, right? And we can say that again because we started at 30 meters per second at the beginning of this. We accelerate down to 0, so our change in velocity, we lost 30 meters per second worth of velocity. So our change in velocity is this negative 30 meters per second. But this is also equal to a3t3. So I can actually come back up here to this equation and rewrite this. Delta x3 equals v0 3 times t3 plus 1/2. I have a3t3 squared. Let's split up this t squared. So we have a times t, but one of those, we can substitute that out. So we have a3t3 times t3. This is, of course, going to be v0 3t3 plus 1/2 delta v times t3. Now what I have is one equation and one unknown. This delta x3, this is 50 meters. This initial speed, 30 meters per second. We don't know the time. I do know the delta v, which is negative 30 meters per second, and then I don't know the time. So let's go ahead and distribute out our time and solve for our time. And then that will be the last thing that we need. Delta x3 equals t3 times v0 3 plus 1/2 delta v. Solve for the t. t3 equals delta x3 times v0 3 plus 1/2 delta v. It's important to keep track of this. This delta v is a negative value, right? So what do we get from this? What does this actually give us? This gives us v0 3, which is going to be 30 meters per second. So we have 50 meters for my distance divided by 30 meters per second minus 1/2 times delta v, right? So I'm going to pull the minus sign out here. So minus 1/2 times delta v. Delta v is our negative 30. I already pulled the negative sign out. So it's minus 15 meters per second. This, of course, is then just equal to, I'll make sure I'm keeping this on the screen as I write this, is equal to 50 meters divided by 15 meters per second. What does this 15 meters per second mean? It seemed like I did a lot of complicated algebra to get to this. What does this really mean? This is actually our average velocity. This is actually me just saying the time is equal to my total distance divided by my average velocity, which of course we know as our other equation. As we said before, this is our other equation that we have. Delta x is always equal to the average times t. You can rearrange that. The t is going to be the total distance divided by the average velocity every single time, right? And again, we know this is the average velocity. Why? Because we have our initial velocity minus half of our change in velocity, right? So again, this one works out in this case since our final velocity is 0, our average velocity is halfway between 30 and 15, sorry, 30 and 0, which is 15 meters per second, right? We started out, if we look at this graph again, let me pull it up. For this last part of the trip, let's look at our v, our average velocity for part 3 would have been halfway between this 30 and this 0. So our average velocity must have been 15 meters per second, which is certainly what we get here. So when we do this, we end up with t3 equals 50 meters divided by 15 meters per second. This gives us about 3.3 seconds. Of course, now our total time, we can just add them all together, equals 6 seconds for the first part, 10 seconds for the second part, 3.3 seconds for the third part, and our total time that we get is about 19.3 seconds.